Okay, we're out of focus. Still out of focus. Get in focus quickly. Out on it. Okay. Okay. Now, if I tell you it's a rubber band chain at a mass of, actually, we can find out what the mass was of this chain. And if it isn't, it doesn't matter. Mass of no, exactly not. Let's just say 30 grams. It came out 28, say 30. Says mass of 30 grams. And we hang at one end. Okay, here we got the chain. And we put a little hook here, a string over a pulley with a 50-gram mass. Okay. Then we conclude that, well, the string has, or the chain has some sag in it. So the tension isn't uniform throughout. Okay. And you can do a little bit of statics and figure out whether the tension's a little greater in the middle or a little less. Well, it turns out that tension here has a vertical and a horizontal component. Tension there in the middle only has a horizontal component, which is going to equal the horizontal component of the tension here. Okay. So tension is going to be a little less out there as long as the sag isn't, as long as this angle here isn't too severe. You kind of assume you have a uniform tension that's equal to whatever the tension is in that string, which is horizontal. You can also conclude the tension in that string is equal and opposite to the tension at the center, or equal in magnitude to the tension at the center. So if the tension at this end is a little greater because it's only its horizontal component that's equal to this, it's also got a vertical component. It's kind of significant to understand that. But bottom line, let's assume the tension throughout is 50 grams. Well, it's equivalent to a 50-gram weight, which means it's half a Newton, doesn't it? Okay, so half a Newton tension and a chain, and let's just say that the length is 5 meters. Okay, so, and I don't really want numbers, but just to give you numbers to 0.5 newtons, 30 grams, and 5 meters. Tell me how I'm going to figure out the propagation velocity. Guess I wasn't recording. It's okay. And I don't remember if I said this. I said, okay, if we know the tension, mass, and the length of that rubber band chain, how do we calculate speed of propagation? Okay. Unfortunately, nobody did. This should be something you've dreamed about at least a dozen times since you encountered it. This is how you calculate propagation velocity. I don't know if I use V or C, often it's C, so I'll use C today. We talked about it last time with that board and everything. Review. Got 5 days between Thursday and Tuesday, plenty of time to review. Make sure you do it. Okay, now given that the tension is a function of length, it's a linear function. It's 0 when the length is less or equal to L naught. L naught being the length at which significant tension begins to occur. Okay. in case it's a proportionality constant. Total mass M. That's enough to determine the frequencies of all the harmonics as functions of L. Now, if you just get f sub n of L, that's a perfectly good function. It tells you what all the rest of the harmonics are. You put that formula into Excel, do a spreadsheet that gives you 10,000 frequencies, most of which would be irrelevant to the rubber band because you're getting down to, well, it doesn't matter. Okay, getting down to lengths where the paper clips wouldn't allow it to produce the harmonics. Okay. There we have it. So that's an assignment. You're welcome to ask me questions outside of class, email me, provide ask me. Okay, tell me what you're thinking. But let's see if we can get some progress on that by next time, but certainly by Friday. And the only way you're going to make good progress on it is to think about it regularly. You put a time limit in yourself. Think about it 10 minutes every day. Here's when I'm going to do it. Okay. Think about it 10 minutes every day, and it'll loosen up your brain and bring the things that I hope you've at least moderately absorbed from the transition problems, where you can answer the question. Okay. The ideas here are very simple, but you got to put them together. So putting them together is not the simple thing. Okay. And to put them together, I mean, you got to understand what a harmonic is. You observed it, you got a good feel for it. I don't think there's any problem with that. But putting it together with what you get from the transition problem might be a little challenging. Okay. Another thing we did last time, we got down to pressure over 3 equals number of particles times the average kinetic energy per particle. I'm sorry. Well, I'll put it here. So it's PV equals 3 N AE bar. That starts, I had a question on that. One of you asked me a question. And I developed it at the end of the class last time, so make sure you understand that development or ask me questions about it. Okay. Also, PV, of course, equals NKP. So what's the average kinetic energy? Well, 3N times the average kinetic energy is N times K times T. Okay, set these equal and divide. You get this is equal to KT over 3. Now we can set this equal to this. Implies this. So 1/2 M times square of the RMS velocity. What's RMS stand for? Not sure I put that in the transition problem. It means root means square. The square root of the squared average, the average square root of the average of the squared velocities. Okay. And I was always a little confused about that because I never saw a really good definition of it. when I learned the stuff. I knew to use it. Okay, and I'm not going to talk about that right now. We'll talk about our RMS once you get everything else down. So there's your BRMS, and there's your definition of K. Then we use NKT rather than NRT. So we talk about the number of particles, bring it down to that. But we talked a long time ago about how K, Olson's constant, and R, the gas constant, Rydberg's constant, are related. Just one is per particle, one is per mole. Okay, so you got that. Now, that's that along with what I developed last time. And I got down to this point and we were out of time. And we're somewhat over time, so we split. That's how it goes together to give you this formula. Okay. Now I think I posed it and I'm assigning it now. Given original pressure, original temperature, original volume. And number of moles, pH, and TC for gas. We're talking about model engine type thing. But now we got some other mechanism to make this thing halfway efficient, but it's the same process. So we go from P naught, V naught, T naught, T1, V naught. I'm going to say P1, V1, T1, P2, V2, T2. Where T1 equals T, sorry, T1 is just T1. I'll use H for the height to which you're going to raise the water. And I'll even give you a hint, but you're going to have to justify. P1 is P naught plus rho GH, and that's just Bernoulli's equation. Okay. And you can justify that in many ways. I'll give you that. And then you don't know what T1 is. You know, over here, just by the diagram, pressure is constant in this direction because this is a P versus V diagram. Okay, which is why V1 equals V naught because you're moving vertically, where V goes that way and P goes this way, right? You know, here's your PV axis. So that clearly in this horizontal line, V2 equals V1, I expect you know why you'll be able to explain that. V2 equals V1. V2 equals TH. T2 equals 1. From that information, which you need to fill in, the area here is the practical work you get out of the cycle. Explain that more later when you work out these details. Okay. And then, of course, we can complete the cycle one way or another. Bring the thing back to its original pressure and then cool it off. Okay. So what happens is expand it, because that's another way you're going to get back to the original pressure. All the things still confined. Okay. Well, actually, not necessarily. You could cool it, but we expand it first, which, if it's an adiabatic expansion, expends some of the internal energy, lowering the temperature. Okay. We do it isothermally. We do it very slowly and keep the temperature the same as it was up here and expand it. We wouldn't generally do that, but we could. And your adiabatic and isothermal curves are a little different. In the isothermal case, temperature is going to be higher at this point than it is in the adiabatic case. So is the isothermal going to be out here, the adiabatic here? Or is the isothermal going to be here if the adiabatic is here? Adiabatic. P v to the gamma is constant. If you know P and V here, and this is the adiabatic curve, then you can calculate PV to the gamma here and get an equation for P in terms of V and integrate that. Okay. And that's pretty simple once you understand this. The gamma is specific heat and constant pressure divided by specific heat and constant volume. That equals 7/5 diatomic five-thirds monatomic, because in the monatomic case, you'll have only 3 degrees of freedom in the gas. And the constant pressure is as if you got 2 more degrees of freedom. I've said all this, so I'm saying it quickly today. Okay, so if you got 3 degrees of freedom and then 2 more for doing the work against constant pressure, your ratio is 5/3. If at constant volume you got 5 degrees of freedom, 3 translational and 2 rotational. Okay, and then 2 more for constant pressure, the ratio is going to be 7/5. That's something you need to digest and understand, because it's real important for understanding where energy goes in this engine. That's why diatomic and monatomic are different. It's because heat up the diatomic gas, you got to heat up, you got to increase translational kinetic energy and rotational. Monatomic, you don't have it, it's easy to heat it up. Okay. So that's kind of a review of a lot of the important things we need to understand at this point. And let me think, I think there's one more. Let me switch my metal gears here for a second. Okay, so nobody was able to answer this question. I said we got, what we did last time, we talked about it. We got 50 joules per minute. That's a ballpark estimate. That could be off by a factor of 2, even way, even more than that. Okay, because we didn't measure very precisely. We weren't able to at that time. Okay, but 50 joules per square centimeter, 50 joules per minute passing through this stack in this direction. And each of these is 20 square centimeters. So my question is, well, how many joules per minute is that per square centimeter? I didn't get an answer. Okay, because people are looking for a formula, I think. Okay. And my thing I urge you to do is don't look for a formula. If you've got this many of these spread out over 20 of these, you're going to divide this many by 20. You're going to divide the number of joules per minute by the number of square centimeters. That's just a simple concept that doesn't require a formula, although the formula reinforces that. Okay? But if all you're thinking is formula, you're not going to understand what's going on. Now, you can use the formulas if you think about what's behind the formulas. If you're just using the formulas because that's how you get the right answer, it's not going to gel for you very well. I don't think. Everybody has different learning styles. I'm urging you to think about the concept before you think about the formula. See how the formula represents the concept. And anytime you think about the concept, think what the formula is. And anytime you see the formula, think what the concept is. It's two sides of the coin that you need to understand if you're going to be able to answer some of these questions. Okay. If you read the transition problems, I explain them in terms of the concept. Then I explain in terms of the formula. You need to understand both facets of that relationship. Okay. Don't be content with the formula because formula is not going to help you conceptually. And don't just be satisfied with conceptual because sometimes you need symbols to help you put the concepts together. Okay. And very often you need both. You need some interplay between both, and whatever works best for your particular learning style. But the thing that gets you the answer as quickly as possible isn't always it. So weigh that out. Everybody's got to make their own decision how they approach things, and everybody has different preferences. Okay. Don't let your preference be the easiest route. Let your preference be the one that gives you the deepest understanding. Okay. And you can get there either way, but you're going to need a combination of both, which is kind of contradictory. I think you understand what I'm saying. Okay, in the case of heat conduction through this stack of plates was by symmetry, the fact that the thing was insulated around the sides, open at the top, and on a ceramic plate, pretty constant temperature on the bottom. We conjecture that the rate of heat conduction per square centimeter is pretty much the same throughout. If I take a metal beam, which is what we call it, it's a piece of shell standard, in a battery, 1.5 volt AA battery, and clamp a wire lead on both ends, and then bring these ends of the lead in contact with the ends of the battery, we're going to get an electrical current, assuming that the coating of this thing doesn't prevent it, and it probably will. Okay, so I'd have to pile off some of the coating and make sure I have good contact. And I think we know enough about electrics to understand that much. Now, what's going to happen when I put this here? Okay, what's going to happen is one thing is we're going to get an electrical field. Now, gravitational field, what's a gravitational field? Well, you got a planet here and you got gravitational forces pointing at the planet. Gravitational accelerations is a function of distance in there toward the center. And the further you are, less the acceleration, and it's an inverse square relationship, right? So you can visualize this bunch of arrows pointing into the center, getting shorter and shorter as you go out. That's a field. Okay. Now, if you had multivariable calculus, you've done quite a bit with electric fields, but some of you were in it, some of you already had it. In this case, it's a force field that accelerates charges as opposed to masses. Okay, well, you're familiar with the fact that, you got protons and electrons, and then you got quarks and gluons and all that stuff inside of the protons and neutrons, right? Okay, you got that whole model, which we think is pretty accurate. So what happens in a metal is, without going into a lot of detail that we're going to later, you've just got some of the electrons that aren't all that strongly attached to any specific atom, although they're strongly held inside the conductor, okay? They're free to move in response to the electric field, okay? Not totally free, because as they move, they encounter other electrons, and they encounter the atoms in the metal lattice, just a regular spacing of iron molecules with a few other things, okay? So they run into those things. They don't exactly run into it's a wave interference. It's a wave phenomenon. I already talked a little bit about waves. We're not going to try to connect that at this point. A little later we will. Okay. So you can think right now of electrons as just little particles that respond to the electric field. The protons do too, but the protons are locked in this lattice in the nuclei of the atoms, and they don't get to move from one place to another, as the electrons do. And that's your electrical current. Now, electrical currents aren't always currents due to electrons, but in metal conduction, they are. In semiconductors, you can have holes, and ionized gases, you can have positive and negative ions moving in negative opposite directions. So it's not always electrons, but right now it's electrons. So right now we confine ourselves to the idea of electrons. Now, the acceleration of the electron depends on what we call the potential gradient. It's a gradient, just like we have a temperature gradient. Okay, so when these things are connected, I'm going to take them off because they get away. Magnets keep sticking to the thing. So across this, you have what we call a potential gradient that we can easily define, and you'll see the definition of the transition problems. The potential gradient's measured in volts per meter. And that's your electric field. That tells you how much acceleration you're going to have for each electron. Multiply that potential gradient by the charge on the electron. You get the force, and you divide by the mass of the electron, and all that is going to come out in the transition problem. Just get a basic idea. The thing I want to focus on is the potential gradient from here to here. Okay. Now, this is uniform metal, so your potential gradient from here to here is constant. Okay. If you have, let's say, Well, let's just pretend if you hook a battery onto this thing, you're not going to have 1.5 volts. Okay. Because there's also potential gradient within the battery. And because this is a good conductor and your battery is a less good conductor, most of the potential change will be within the battery if you hook up to something like this. Okay. So you might have you might have a millivolt between here and here. Analogous to the fact that we have what? A change in temperature from 110 degrees down to 70 degrees or whatever, okay? Throughout those metal plates. It's totally analogous. We're also going to have then a current in response to that potential gradient. The thermal current is in response to potential gradient. If I have a stack of plates twice as high, potential gradient from 110 down to 70 degrees, if those temperatures remain the same, and we can pretty much make it so, potential gradient is only going to be half as great, right? If the potential drops over twice the same potential change or same temperature change over twice the distance, we're going to have half the gradient. Okay. Well, anyhow, so let's say we have a millivolt over this distance. What's this distance? It's 2 feet, which is ballpark 60 centimeters, very close, 60.96 or something like that. That should be 61 point something. I think it's 30.48. Well, some sort. But anyhow, 60 centimeters. So let's just make the numbers easy. Let's say I have 12 volts over 60 centimeters. What would be the potential gradient? Well, change of potential is 12 volts. (60 centimeters), 12 divided by 60, right? 0.2 volts per centimeter. Turns out to be 0.2 newtons per coulomb of charge, and it probably won't be that great in this thing, but yeah, figure that out later. Okay. We need a bunch of other stuff to figure that out. All right. The other thing is that due to the fact that electrons repel each other like crazy, the potential gradient is going to be the same everywhere at any distance from the end. In other words, through the vertical, through the horizontal, through the other vertical edge of this thing. The massive repulsion of the electrons to one another is going to guarantee that your current density is very, very nearly uniform throughout the cross-sectional area of this thing. Cross-sectional area being just the area of what you see if you look at this thing directly on the end, okay? The area of that little U-shape. Make sense? So there's an analogy between something you've had your hands on and understand pretty well. And something that's a little harder to understand. So the central concept in conduction is going to be several concepts: potential gradient and current density. Okay, so I'm going to. Uh-oh. More than I thought I did. So with heat, you have rate of heat flow over cross-sectional area. A very simple concept that's easily understood in terms of that stack of plates. Proportional to the temperature gradient. And I want to define temperature gradient. Since it's already been defined and you're really supposed to internalize that idea. And you probably have if you've been thinking about this situation. If not, make sure you really understand it. It's really fundamental and it's amply represented in the transition programs. Then we have electrical conduction. Current density is just current over cross-sectional area. It is proportional. Potential gradient. Like volts per unit of length. It's measured in units of volts per length. Turns out to be equal to the force per unit of charge. Okay. Volts per unit of length is easy to understand. We just looked at that bar. So if you've got 1.5 volts over the bar, divide that by the 60 centimeters, gives you 0.025 volts per centimeter, I think. Okay. I might have done that totally wrong because I didn't even check it in my head, but so that's really easy to understand. This is easy to understand. Why is that equal to force over charge? It's not hard to understand, but I'm going to leave it to the transition problems to make that clear to you. Okay? Make sense? Okay. Well, ponder that for a minute. Let me check something here. Just in case this was out of focus, as I was saying it, there it is in focus. Now, a couple of points I want to make. Okay, here again, we have a conductor. Okay, might be an insulated conductor because of the coating, but it's conductor. There are a bunch of free electrons in here. A really huge number of free electrons. Okay. Now I'm going to use simple numbers, but the numbers that we're talking about actually are in the order of 10 to the 20th, give or take a few orders. Okay. let's just say that I had 1,000 free electrons in here. And they were moving across here. How fast do you think the electrons move? We probably think they move fast. Yeah, they do. They're thermal. You do the square root of 3/2 kT that we just talked about for an electron. The mass of an electron is almost 2,000 times less than the mass of a proton. Okay. You know, ballpark 1,800 for protons and neutrons, but slightly maybe for neutrons. Neutrons are a little more massive. But what happens is they're bouncing off of things all the time. Okay. You also can calculate the acceleration of an electron, and you will. Okay. The acceleration of an electron is so great that they would get to the speed of light in 1,000th of an eye blink, something like that. Okay. Of course, I can't get a speed of light because their effective mass increases exponentially. Well, increases as it approaches speed of light, and the integral of that thing from 0 to infinity is infinite, or to 0 to it's. I could write it all down. It's just relativistic mass change. Okay. And I could write down the expressions and stuff. We're not going to bother with that today. In any case, yeah, they get up to, a significant fraction of the speed of light very quickly. But well before they got to the speed of light, they bump into something and rebound that way, about as likely as they rebound this way. Of course, they can rebound in any direction. So their progress from here to here keeps getting impeded by the material. Okay. Again, it's wave interference stuff, and I can't give you a really good deep explanation of that. We can see some of it. So it turns out that the electrons in a typical circuit in your house are moving at speeds that you measure in millimeters per second. Okay, that's on the average. It's just like you got this cloud of electrons in here. There's so many of them that they don't have to be moving very fast to carry a huge current. Okay. And we can work out those numbers. Those numbers are easy to work out once you understand the concept. Like in copper, you got a certain density, certain molar density. Okay. It's around 50 something, I think. That may be iron. Anyhow, I don't remember what those numbers are. Things are slipping away from me, but from the mass density of copper and the fact that each copper atom can contribute 2 electrons to the conduction band, I think. Okay. You can figure out how many electrons are available in that copper. Then once you know what an amp is, you're running 15 and 20 amp circuits in your house probably with 12 gauge wire. You can run 15 amps and 14 gauge wire, but 12 gauge is better. Okay. Getting a drift of a few centimeters per second and putting one end of that terminal in this hand and one end of the terminal in this hand, going to make you feel bad. Maybe to the point where you can't let go. Maybe the point where it fries you. Okay. Now at 120 volts, probably not. But okay, so anyway, all that stuff goes together. All that stuff is really pretty easy to define and gets defined in these transition problems, and then we do stuff with it. Okay. So now let's get back to my point. If I've got 1,000 electrons in here and they're moving at 2 centimeters per second. Okay. Then my question is, how many electrons pass this point right here every second? So I've got 1,000 electrons. E minus is kind of a standard notation for an electron. 1,000 electrons. Then how many electrons per second pass a given point? Okay, so what's your picture here? So electrons are moving at 2 centimeters per second, right? And there are 1,000 electrons in 60 centimeters. Now, two ways I can think of to do this, okay? If electrons are moving at 2 centimeters per second, then all of them are going to go from here to here. All 1,000 of them are going to go from here to here in 30 seconds, right? That's easy. 2 centimeters, 60 centimeters. Got to move for 30 seconds, okay? So you're going to have 1/30 of 1,000 passing at any second, at any instant. Another way to look at it, how many electrons are there in a 2 centimeter segment? Well, 1/30 of the number you have in a 60 centimeter segment, which is 33 1/3, okay? And they're all going to pass in a second. Either of those is an image you can use to figure this out without having to look for a formula, okay? And that idea goes into some formulas. They may be a little more complex, but still not very hard to understand if you think in terms of what's going on in front of you, okay? Very simple reasoning. You can determine a whole lot. Now, in here you've got a cloud of electrons, okay? This is probably 3 or 4 moles, okay? It's iron, and I don't remember what the valence of iron is now, but assuming you got 1 electron per atom, then you got 3 or 4 moles of atoms. Oh, well, you got 1 for every atom, okay? You got 3 or 4 moles, which is about 10 to the 20. Well, it's about 2.5 times 10 to the 24th electrons, okay? It turns out that we can define, and you don't need to write this down, you have it right there in the problem sets. I think I'll double check and make sure, but you have approximately 6 times 10 to the 18th electrons per second, okay, is an atom. Now, we got 10 to the 18th, we got 10 to the 24th. Okay. That ratio is approximately 1,000,000 to 1. Okay. So how fast do the electrons in here have to be moving to give you an amp? 1/1,000,000th of whatever, 1/1,000,000th of this length per second. Okay. It's not very fast. Now, my numbers might be off there because something doesn't seem quite right about that. Seems a little slow. but I don't really see much of anything wrong with it. Okay. Yeah, that just means that maybe I'm just being stupid. I was thinking intuitively, they're moving a little faster than that. What you visualize then is a cloud of electrons, an electron cloud, because they kind of make a cloud that gradually migrates from one end of this thing to the other. Okay? Just like in a cloud, you've got water droplets. Clouds moving along, not all at, walking speed or whatever, but the water droplets are bouncing around at, 100 miles an hour. Okay? Bouncing off of each other and stuff. The tiniest droplets. Okay? Probably wouldn't be moving that fast, but they're moving a lot faster than the cloud is. Well, you got electrons in here, they're moving thousands of meters per second because of thermal energy, 3/2 kT, square root of 3/2 kT. You can work that out and find it easily. So they're moving like crazy, but the cloud as a whole is just drifting slowly. And of course, if you have to have a complete circuit, no, you have to have a source over here that's driving this. Okay. Otherwise, the electrons would congregate at one end and repel all the electrons they're trying to get there, which means that you'd have no current at all. Okay. And it comes down to that. We'll talk more about that, draw some pictures. Make sense? So again, we think of conduction, you think an electron cloud, and you think, where'd I put it? Current density. Okay. And the current density, I already said, is proportional to the potential gradient, which is the number of volts per meter. Assuming a constant cross section. Actually, don't even need that. If you don't have a constant cross section, just like in a fluid, you narrow things down and things have to move faster. Okay. You have fewer electrons per unit of cross-sectional area, they got to be moving faster, just like in a fluid. Make sense? You understand the analogies that are involved in everything we've been talking about and in the transition problems? There are a bunch of analogies on fluid, thermal conduction, electricity, and then within all those topics. And you want to try to understand those analogies. Okay. Okay, so there are only 5 problems in set 2 of the transition problems on electricity. Okay. You go to that set and nail those 5 problems. Okay. Make at least a good start on that by Wednesday so I can start asking you questions. And maybe start talking about some of the other longer sets. Okay. Some of what's behind stuff that you see, because we're starting with a conduction model. Typically, I would start with the same thing that textbooks usually start with, which is Coulomb's law. So you probably ought to just refresh yourself on universal gravitation and orbits. Okay. Makes sense? And I'm just talking about a 15-minute refresher. Centripetal force equals gravitational force, right? Energies, okay, potential and kinetic energies. And, you all took a final pretty recently, so you should be pretty well versed on that. Still refresh yourself, okay? And then you probably find the first part of Coulomb's law stuff to be pretty straightforward because it's almost totally analogous to gravitation. Then we go into other things and connect that with everything that we're talking about today with conduction and with fields and kinds of neat stuff. Okay.